Alright, so today's lesson you don't have a handout for. This is sort of an extension on quantum information that I mentioned yesterday. We're going to talk about cryptography. I'll explain the basics, and today I'll give you a little activity on just basic classical cryptography, and tomorrow I'll give you a little activity on quantum cryptography, which is fun, so do it with maybe a sibling or a parent. So let's start with cryptography. So how does that work? So let's say we have Alice. Alice wants to send a message to Bob. So what's Alice going to do? They're going to create a key. And so Alice is going to take her message, put it in the safe with the key. There might be an eavesdropper, but that eavesdropper, without a key, can't get into the safe. And so the safe goes to Bob, he uses his key, and gets the message. Okay, so how does this actually, what's an example of this in action? One is called a Vernam cipher, and we're going to use binary. If you haven't learned what binary is, it's pretty simple. It's just numbers 1 and 2. I mean, why do we count to 10? Right? Why don't we count to 8 or 16 or just 0 and 1? And that's all binary is. And so we have 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. But then also 1 plus 1 is 0. Remember, there's no 2. Right? We only have the numbers 0 and 1. So they have a key. And the key is both the same. And for example, let's take this key. Then Alice prepares a message. Just for reference, a message this long in binary is probably 1 character. Right? Maybe J or K or something. Then you're going to add those two together. Okay, so again, 0 plus 1 is 1, 1 plus 1 is 0, 1 plus 0 is 1, and so on. And that's going to give you an encrypted message. Now you can send that encrypted message. An eavesdropper could look at it, but they won't know what it means without a key. When Bob gets it, he uses that same key and again adds them. And when he does that, he gets the original message. Okay. So this seems pretty secure. Okay, there's a couple things we want to go over. One, if the eavesdropper intercepts the cipher or the encrypted message, what's the only way she can recover the original message? Well, she needs a key. And for a 16-digit key, how many different keys does Eve need to try? Right? Even if she tried some random key and got the message to be hello, can she be sure that's the actual message? There's so many other keys that can actually create a word. So you can't be sure that's a message. Right? So it seems pretty unbreakable. But there is a problem here. The problem is, how does Alice get the key to Bob? That's the problem. Right? If Alice simply sends the key, well, the key can be intercepted by an eavesdropper. And then what's the point? So this is where computational security comes in. So when you do online banking, for example. Now, if you're going to take a message and you're going to encrypt it, all you need to do is multiply two 200-digit prime numbers together. And that's fairly easy to do. Not in your head, but at least for a computer, it's fairly easy to do. What's hard to do is then to unlock this, you need to figure out, being given one 400-digit number, you need to figure out the two 200-digit prime numbers that multiply to give that 400-digit number. That's hard to do. I don't think you can do it. Computers can't even do it. Okay, it's a very, very, very hard mathematical problem. And that's what security is based off of. Right? Private information is simply based off of the fact that you can't do a hard math problem. It's not perfect though, because you can copy the message and spend time breaking it offline. Right? So again, not perfect, but extremely difficult to crack. So what we're going to do is we're going to create a different type of key. It's going to be called a quantum key or a quantum key distribution. And we're going to go over how this works. And how is it going to work is, well, quantum mechanics, or the rules of quantum mechanics, are going to come to the rescue. Specifically, we have wave collapse, meaning if you try to measure, if an eavesdropper tries to measure an unknown quantum system, they will change the state of that quantum system and will therefore be detected. Next, the uncertainty principle. Even if they try to obtain information from a quantum state, the uncertainty principle says they cannot obtain all the information from that unknown quantum state. So not only will they be detected, but they can't get all the information anyways. Right? And there's no way around this. These are laws of nature, laws of physics. You can't break those. And lastly, one that we haven't talked about is the no cloning principle. The no cloning principle says it is impossible to copy an unknown quantum state. So they can't copy this unknown message and try to break it offline. They can't do it. Okay, so it seems pretty much impenetrable. Okay, and this has been around for quite a long time, and a lot of people are still researching it. So let's see an example of how this quantum key distribution is going to work. And since we're so familiar now with polarization, let's use polarization. So again, recap. We can look at, say, the HV basis and have something horizontally or vertical polarized, or we can look at the plus or minus 45 degree or the diagonal and anti-diagonal basis and measure it in that. And since this is binary, what we're going to do is, let's say a horizontally polarized photon or a diagonally polarized photon will give them the information of 0. For a vertically polarized photon or an anti-diagonally polarized photon, we'll give the information of 1. Okay? And that we can clearly tell everybody. It doesn't matter if they know that. Now here's what we're going to do. That's a lot of steps. You can go back to the PowerPoint and look at this. But I'm going to sort of go over it with our example, Alice and Bob. So what happens? Alice chooses a random piece of information that she wants to send. And remember, we're not sending the information. We're not sending the message. We're trying to send the key. Right? The message can be later sent using the Vernam cipher. We're going to need a safe way to send the key. So the first piece of information we're going to randomly choose as 0. All right. Then we need to randomly choose a basis to encode that in. Let's say Alice randomly chooses the HV basis. Well, what's the value of 0 in the HV basis? We chose that to be horizontal. So Alice sends a horizontally polarized photon over to Bob. Now Bob randomly chooses a basis to measure that photon. And let's say randomly chooses the HV basis. Well, if he chooses that, he will make a measurement that it's horizontal, and he will determine that information is 0. So let's repeat this. Let's have 1. Okay, she'll choose 1, encode it with the HV basis. 1 is vertical. But let's say now Bob randomly chooses to make a measurement in the diagonal anti-diagonal basis. Well, what's a vertically polarized photon in the DA basis? Well, it's going to be some random result. We don't know because it's in a state of superposition. Okay, so whether you get 0 or 1 will be completely random. And then we continue. I think you get the idea. So I'm going to go through it there. And this is the information we have. Now what's going to happen is, what happened? Everything's going to disappear. There we go. So now what's going to happen is Alice is going to get on the phone with Bob, and they are going to compare. Now they don't have to compare. This is a very short example. I don't know how many pieces of information I have. 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of information. Really, you would have thousands or millions of pieces of information, most likely even more. And you would choose a certain percent of it, not all of it, but a certain percent. and you will openly share. And so what Alice is going to do, Alice is going to say that I made a measurement for the first one in the HV basis. And then Bob will say, I also made a measurement in the HV basis. And then Alice should say, well, then you got 0. And Bob said, yes, I got 0. And then Alice is going to say, well, I made a measurement and HV basis for our second bit. And Bob's going to say, no, I didn't do that one. Okay, so whatever you get is going to be completely random. Let's scratch that. We are not going to consider that. So what they do is they go over and they compare to see where they made the same, or where they used the same measurement basis. Okay, and the areas where they use the same measurement basis, they will keep. Then they can share after that what those values are. Now this is open, right? But remember, this is only a small portion of the information. Now, why would they share that small portion of information? Let's look at the case where we have an observer or an eavesdropper. All right. So Alice prepares that first bit. Then the eavesdropper has to measure it. She doesn't know what to measure it in. So let's say, for example, she measures it using the DA basis. Well, she'll get some random result. She'll send that over to Bob. Bob is measuring it with the HV basis, but now it's being sent as either diagonal or anti-diagonal, which means Bob will also now get some random result. And that means she has changed. The eavesdropper has changed. Now, how is she going to be detected? Let's get to that later. Let's say we just continue this. Alice sends the next piece of information, and the eavesdropper measures it. In this case, again, some random piece of information. Now, there are areas where maybe the eavesdropper doesn't get a random piece of information, like here. She uses the same basis in our fourth bit, okay? And so she will actually get that bit, and it will be sent off to Bob. Right? There'll be other places where in the second last one, she will get that bit, but Bob doesn't. All right. So let's go back to the phone call. Alice calls Bob, and they compare the basis on which Alice prepared it and Bob measured it. Now these are the ones that are all the same. Okay, the first one is both HV, the next one is both DA, the next one is HV. So these are the pieces of information they want to keep. The rest are discarded. But then they're going to choose a small portion of it. Let's say this is the small portion they've chosen out of millions of bits of information. And Alice is going to say, okay, so the first 5 pieces of information then is 0, 1, 1, 0, 1. Now Bob is going to say some random numbers, and then 1, 0, and then a random number. Now it's possible 1 or 2 or 3 of those random numbers happen to be all the same. But when you look at this as a large scale, if you have a trillion pieces of information and you share 100,000, the odds of them all being the same are pretty much 0. And so what's going to happen is they're going to start to realize, no, we have different numbers here. Well, how is that possible? Well, because somebody's listening in. Okay, and so the eavesdropper is detected, and the eavesdropper clearly also has a whole bunch of random areas. So the eavesdropper didn't even get all the information. Okay, so quantum protection in quantum cryptography. All right, so that's all I want to go over for that. Try the classical examples I'll give you today about some basic cryptography. And then tomorrow I'll give you a little activity that you can do with your sibling or parent on quantum cryptography. Okay, and after that, have a good weekend.